Hi students, we have been learning about infrared spectroscopy. There we are learning about uh, qualitative relationship between force constant and bond energies. Uh, Already we have derived a equation to identify the vibrational frequency of a single covalent bond present between two atoms with the help of Hooke's law. That thing we have studied about in previous class. Uh, So how the force constant is influenced by the bond energy and different types of covalent bonds, how they will uh, contain different vibrational frequency values. So force constant in relation with bond strength that we have studied in previous class. Here we can see single bond, double bond, and triple bond. Single bond contains the more bond length value, so that bond energy is more shorter. Bond length is shorter one, so bond energy will be more. This thing we have studied in previous class. So with the help of this equation, Hooke's law, that is nu bar is equals to 1 by 2 phi by c, 2 phi by c, k by nu. This is the equation to identify to calculate the wave number or the vibrational frequency for a covalent bond. Either it may be a single covalent bond, double covalent bond, or even triple covalent bond also. Wave number of the radiation is inversely proportional to the reduced mass, so that once the reduced mass is less for a covalent bond, vibrational frequency will be more. The reduced mass is more, so that the vibrational frequency value will be less, because vibrational frequency vibrational frequency, in the sense the amount of uh, mm, the amount of energy needed from the radiation. So that is simply we can say uh, wave number. How much wave number containing radiation is making a covalent bond to participate in bending vibrations, even stretching vibrations. That is the number we will express in terms of vibrational frequency. Of course, wave number and frequency of the wave, they are internally related with one another. They are in direct proportional relationship. So frequency of the radiation is directly proportional to the wave number, so that once the vibrational frequency or the amount of energy needed for the vibration of a covalent bond is more, wave number is more, and vibrational frequency value will also be more. So we can calculate the amount of energy required for the vibration of a covalent bond present between two atoms in vibrational frequency values. Even we can also identify that in wave number value. Even we can also convert that one into wavelength values also, lambda values also. So these are the uh, points we have learned in previous class. So value of vibrational frequency will depends on two factors. One is bond strength and another one is reduced mass. Bond strength is directly proportional to the vibrational frequency or wave number of the radiation that is required for the vibration of bond. Reduced mass is inversely proportional to the vibrational frequency or wave number. Energy also, energy of that radiation also. Yesterday we have learned about this calculation. So carbon hydrogen single bond stretching frequency is 3100 centimeter inverse. So this is the information we have discussed in last class. Today I would like to discuss about the selection rules in infrared spectroscopy. At the same time, I have told that molecules at low temperature, they will exhibit the means the chemical bonds present between the atoms of molecule, they will exhibit harmonic motion. Harmonic motion, so that we can consider, we can apply the properties, we can easily assume uh, a single covalent bond movement, a stretching vibration or bending vibration, as similar with simple harmonic oscillators motion. A simple harmonic oscillators motion. Once the temperature is raised, or temperature is more, or the molecules contains more energy, they won't follow the uh, we cannot apply whatever the uh, properties that we observe for the simple harmonic oscillator. We cannot apply, or they are not means the molecule, it will deviate from the s- uh, it will deviate from the simple harmonic oscillators motion, and it will attain the anharmonic motion, where different parameters come into the picture. And in such cases we will find some other kinds of bonds. What are that bonds, we will discuss in coming slide. Okay. During the anharmonic motion, if a bond is in anharmonic motion, harmonic oscillation model good at lower energy, harmonic oscillatory motion containing object is good and easier to apply their properties to the stretching and bending of the covalent bond present between two atoms at lower energy level. Lower energy level means the energy levels present between the same electronic level. Between same electronic level means ground state electronic level and first excited state electronic level. Generally, electronic levels contain the vibrational levels, as well as vibrational levels contain the rotational levels. So the lower vibrational levels means V0 or ground state vibrational level of ground state electronic level, even first excited vibrational level of a ground state electronic level, or second excited vibrational level of a ground state electronic level, or even sometimes third excited vibrational level of ground state electronic level also we can say, right? But did they these harmonic oscillatory motion, or the harmonic oscillation model is not good at high energy levels. If you go for V4, V5, V6 or Vn level of the ground state electronic level, we cannot, it is not suitable to apply the theory present behind the harmonic oscillator model to a chemical bond. So the molecules present at ground state electronic level, at ground state vibrational level, if the sufficient or more and more energy is provided to them, they will undergoes to the excited state, where the exit states will be V5, V6, V7. Of course, it is it is the means promotion of molecule, or excitation of molecule to V6, V5 is very rare one, but sometimes may takes place that kind of transitions. So if that kind of transitions happens, if that kind of excitations takes place, so molecule will be like a object which is undergoing to the anharmonic oscillations. So harmonic oscillator model is good at lower energy level, but it is not good at higher energy level due to atomic repulsions or attractions. For suppose whenever atoms approaches to each other, for suppose atoms approaches, if they cross the barrier where the repulsive forces come into the picture. Therefore, Coulombic repulsion forces, they add to the bond force, making energy increase the greater. See, these repulsive force will also add it to the vibration of a bond, so the energy will be more than it is harmonic. As atoms separate, it is harmonic. The means harmonic oscillatory motion properties we can apply here. As atoms separates, approaches dissociation energy and the harmonic function required, harmonic function rises quicker. So for suppose a single covalent bond length is carbon carbon single covalent bond length is 1.54 angstrom units. Once the bond stretches beyond that 1.54 angstrom units, there will be a bond breakage between the two atoms. So such type of deformations or such type of uh, stretchings are not suggestible, means the energy will be provided to the molecular vibrations is in the range with that radiation. In the range means the range of radiation by that radiation by absorbing by the molecules, they should not undergoes to the bond breakage. They should not undergoes to bond breaking process. Right. See here previously also we have discussed about this diagram. In this diagram, the dotted line indicates the harmonic oscillation, where the line, a simple normal line graph will indicates the molecule which is performing the oscillations or which is performing the vibrations, which are very similar with anharmonic oscillator. So this is the this is the graphical representation or energy levels of different vibrational levels, energy of different vibrational levels, where the molecule is performing anharmonic oscillations. Right. Because of anharmonics, at lower energy difference value, the promotion or demotion of electrons takes place, or promotion of molecule or demotion of molecule will takes place between 2 to 3 vibrational levels. This kind of vibrations will be observed, which causes the appearance of overtone lines at frequencies at 2 to 3 times the fundamental frequency. In general, the vibrations they have to take place with between the vibrational levels plus or minus 1. For suppose this is the V0 level, the energy level, ground state vibrational level. This is first exit state vibrational level, and this one is second exit state vibrational level. So the molecule present here, if it undergoes to the vibrational transition to the V1, that is allowed one at the same time, this is the fundamental vibrational transition, fundamental vibrations actually. For suppose the molecule presented V0 level, V0 ground state vibrational level of first electronic or ground state electronic level, if it participates into vibrational transition to the second excited vibrational level or third excited vibrational level, such type of translations they will produce overtone lines or overtone bands actually. So promotion of molecule from ground state vibrational level to first excited vibrational level is uh, a fundamental vibration. That is a fundamental vibration. Whenever the molecule undergoes to the vibrational transition from ground state vibrational level to second excited vibrational level or third excited vibrational level, the energy difference will be more, and this type of vibrations are not fundamental vibrations, fundamental bands. They are overtone bands. We will call them as overtone bands. This kind of overtone bands will also be appeared in the spectra of infrared spectra of molecules if they undergoes this kind of overtones or vibrational transition between higher energy vibrational levels. Right. So up to this point, up to the previous point, we have discussed about uh, harmonic oscillatory motion of objects, how they are similar with the vibrations of covalent bonds present in the molecule, and at what condition the harmonic oscillatory motion is uh, uh, eliminated, in which conditions, and what type of circumstances they have to be there with the molecules to obey that molecule, the motion of harmonic oscillator. So deviation from the harmonic oscillators, what they causes and what kind of overtones they will have, they will appear in IR spectroscopy, we have learned. And the important point that we are going to discuss is selection rules. I've been saying that in every spectroscopy, if you take, there must be selection rules. Molecules uh, which are given for the recording of spectra, they have to definitely follow some selection rules. So here, in a case of infrared spectroscopy, the selection rules are, we will discuss in this slide. What vibrations changes the dipole moment? Yes, day before yesterday also, I think it is in the infrared spectroscopy 3. You can find that chapter in my channel, infrared spectroscopy 3. In that video lesson, I have discussed about dipole momentum of the molecules. So dipole momentum is a property of polar molecules. Polar molecules are the molecules where we will find the electronegativity difference between the atoms. So if it is more than zero point 0.5, and that if it is more than zero point 0.5 means the electronegativity difference between the two atoms which are bonded with a single covalent bond is more than zero point 0.5. Therefore the covalent bond is polar covalent bond. So if the electronegativity difference is huge in the sense zero point 0.5 to 1.7, 1.7 is highest. If a bond contain the electronegativity difference value is equals to 1.7, that would be the uh, very polar bond. Very polar bond, the molecule's polarity will be very huge. If the polarity is beyond the 1.7, then moreover that bond will come under ionic bond. So polar molecules, they contain the dipole momentum. So what vibration changes the dipole momentum of a molecule? Symmetrical stretching. There are two types of vibrations. One is bending vibrations, another one is stretching vibrations. Even stretching vibrations again classified into two types: symmetrical stretching vibrations, asymmetrical stretching vibrations, and bending vibrations again classified into various types. We will discuss that. Is that discussion is would be very much interesting, and I would like to show you animated images regarding to different kinds of vibrations that are possible in molecules in infrared spectroscopy. Later we will discuss about them. Right. Symmetrical, asymmetrical stretching or bending vibrations and internal rotation about it molecular axis, they change the dipole momentum of a molecule. Dipole momentum means the molecule containing two opposite charges, partial negative charge and partial positive charge. Partial negative charge in the sense, the atom which is with partial negative charge will absorb the electron density slightly more towards it. Therefore the little excess amount of electron density will be accumulated towards that atom in the molecule, and other part of the molecule will attain the partial positive charge nature. Positive charge nature in the sense, the atoms where they are situated toward the partial positive size, they loses the electron density to the more electronegative atom of that molecule. So the more electronegativity containing atom will take or absorb the electrons because of its electronegativity, so that slight excess amount of electron density, it's a partial electron density, not complete or not permanent electron density. That we have to remember. A partial electron density will be accumulated towards the more electronegative atom of the molecule, so that there we will get the partial negative charge. So if this kind of situation rises in the molecule, so the molecule will be a polar one. Definitely the molecule contain some net dipole momentum, so here, symmetrical stretching and bending vibrations are IR active. Asymmetrical, they are not symmetrical. Asymmetrical stretching or bending vibrations, they are infrared active, because in asymmetrical stretching as well as in asymmetrical bending vibrations, the dipole momentum value of the molecule will be changed, so that what kind of transitions or what kind of vibrations they are bringing change in the dipole momentum of the molecule, that vibrations are IR active. For suppose, if you take in the case of symmetrical stretching and symmetrical bending vibrations, of course, even though the molecules are polar also, but if there is no change in the dipole momentum value, but the dipole momentum value, such type of vibrations, they won't appear. Such type of vibrations will not be recorded by the infrared spectrometer. So simply to say, asymmetrical stretching and asymmetrical bending vibrations are infrared active, so that we will see the bands regarding to that kind of asymmetrical stretching and asymmetrical bending vibrations that are taking place in the molecule. Wherever the molecule, even though the molecule is a polar one, but the vibrations are symmetrical stretching or symmetrical bending, they won't exhibit the bands in infrared spectroscopy. Let us see here. If you take the molecule as a hydrogen or some other molecules, the two balls that are attached to a spring can be considered as atoms. The spring between the two atoms can be considered as a single covalent bond, so that the molecule, the animated image will show you the molecule, how it undergoes to stretching vibration, how it is undergoing to the stretching vibration. For suppose, right here you can see the bending vibration. For suppose, if you consider this molecule as a H2O, actually hydrogen atoms, they contain very smaller size, very smaller size compared to the oxygen atom, so that the green balls, they have to be in smaller size compared to the red ball, which we are considering as a oxygen atom. So the springs present between the atoms, they can be considered as covalent bond. As already we know that oxygen atoms electronegativity is more, that is 3.5, whereas hydrogen atoms electronegativity is less, that is equals to 2.1. So electronegativity is difference is 1.4. A huge polar covalent bond, a huge polar single covalent bond present between oxygen and hydrogen atom of water molecule, so that dipole momentum will be there. The molecule contains dipole momentum value. Got it? Okay. So whenever this molecule absorb the energy from the infrared radiation, and again it will undergoes to the stretching and bending vibrations. So symmetrical stretching vibration takes place, asymmetrical stretching vibration takes place, as well as symmetrical bending and asymmetrical bending type of vibrations will also takes place. Right. Okay, let me explain few more information, little more information regarding to symmetrical stretching and asymmetrical stretching here. For suppose, this is the carbon dioxide molecule. Let me explain the example. C double bond O, and here also it's a linear molecule, and very easier to understand the stretching vibrations that are happening in the molecule. For example, if we consider the bond distance is, um, for example, it is not the experimental value, just I am taking as a just for to say to our convenience to easily understand, the bond length is if it is 2 angstrom units, for example 2 angstrom units. Here also the bond length is 2 angstrom units, 2 angstrom units. So here during its asymmetrical stretching means symmetry properties of the molecule will not be retained. Symmetry properties of the molecule will not be retained during its stretching vibration or bending vibration. So the symmetry property here that we have to discuss exclusively is center of symmetry of a molecule. There are 4 symmetry elements. Generally the molecules are classified into 2 categories. One is symmetric molecules, another one is asymmetric molecules. Symmetric molecules means the molecules contain the any one of the symmetry element in them. They are called as symmetric molecules. If the molecule does not contain any one of the 4 symmetry elements, that molecules are asymmetric molecules. All optical isomers, all optical isomers are asymmetric molecules. D glucose, L glucose, uh, uh, even D lactic acid, L lactic acid, means the isomers having optical activity property, they are asymmetric. They won't contain the 4 symmetry, any one of the symmetry element of 4 symmetry elements. That 4 symmetry elements are plane of symmetry, axis of symmetry, center of symmetry, and the fourth one is improper rotational axis of symmetry. What are the symmetry elements? Plane of symmetry, axis of symmetry, center of symmetry, and fourth one is improper rotational axis of symmetry. So here we have to discuss about the symmetry property or symmetry element, that is center of symmetry. Center of symmetry in the sense, for suppose if I let me explain the center of symmetry by taking one example so that it would be very easier to you people to understand. Here I am taking a compound of trans dichloroethane. Trans dichloroethane. This is one chloride and this is one chloride. And here it is hydrogen, and on a next carbon atom we can also find one more hydrogen because it is in a trans geometrical relationship. So these two chlorine atoms are trans to each other. This is a alkene. Cis trans isomerism rises in a case of alkenes only, in a case of alkenes. Okay, here this is the center point of the molecule. This is the center point of the molecule. From this center point I am extending a hypothetical line to the chlorine 1, and again I am doing same thing, that is I am also extending a hypothetical line to the chlorine 2 from the center point. If I uh, if I reach the two chlorine atoms on opposite sides at same distance, for example if I extended a hypothetical line to the chlorine atom, if I reach the chlorine atom at uh, 2 centimeters, for suppose molecules, they don't contain the length, they don't contain the bond length or distances in centimeter scale. For our convenience I am explaining, don't think it as a correct value. If I am even in a next case also, if I am extend a line in opposite direction to the chlorine 1 to the chlorine 1 to the chlorine 2, if I reach the chlorine 2 atom at same distance also, if I reach the chlorine 2 atom at the same distance, if molecule contains such type of property, such type of atoms at same distance in opposite direction, that molecule is said to be contain center of symmetry. That molecule contains the center of symmetry, or uh, uh, center of inversion, also we will say centrosymmetric molecule. That is, here anyway the two chlorines are distributed or bonded at same distance from the center point of the molecule, so that these hydrogen atoms also we will get at the same distance. Therefore the molecule is with center of symmetry. From the center of the molecule, if we extend the lines in opposite directions, if at the same distance, if the two similar atoms are reached, in the case of alkene molecules, we will say that the molecule will be a centrosymmetric molecule, or the molecule contain the center of symmetry. So if the center of symmetry is disturbed during the vibration, that vibration is called as asymmetric vibration or asymmetric bending vibration. Uh, During the, of course, asymmetric vibration, we will say during the vibration, the center of symmetry of the molecule is disturbed. That vibration is called as asymmetric vibration. Either it may be a stretching vibration, or it may be a bending vibration. Stretching vibration or bending vibration. So in a case of asymmetrical stretching vibration, let us see here, during the stretching vibration, if this oxygen atom stretches to 5 angstrom units, for example, if it is stretching to the 5 angstrom units, and if a second oxygen atom, if it is stretches to 3 angstrom units, where from the center of a carbon atom, center point of the carbon dioxide molecule. So here this oxygen atom is undergoing to the stretching at a distance of 3 angstrom units. This oxygen atom undergoing to stretching at a distance of 5 angstrom units. So this is moving little closer, little distance, whereas this oxygen is moving little more distance from the center point of the molecule. So this kind of stretching is called as asymmetric stretching. What stretching it is? Asymmetric stretching. So in this kind of asymmetric stretching, the center of symmetry of the molecule is disturbed. The center of symmetry of the molecule is disturbed. At the same time, we can also find the change in dipole momentum. We can also find it in the change. We can also find the change in dipole momentum value of that molecule. So that mu does not equals to, or mu is not equals to 0. It will not equals. It will not be means the value, we will get some positive value for that molecule, for positive dipole momentum value for that molecule vibration. So this is about asymmetrical stretching. Even during the bending vibration also, if you take water molecule, so here it is hydrogen atom, and here one more hydrogen atom. So during the bending vibration and hydrogen atom, they are both atoms, they are bending closer. These, for suppose here these two hydrogen atoms are situated like this, if they bend towards them, so one hydrogen atom bends very closer, and hydro or either another hydrogen atom, if it bends little closer to center of the molecule, such kind of bending can be considered as asymmetric bending vibration. And that vibration, they bring change in dipole momentum of the molecule, even center of symmetry of the molecule. So means they won't contain the center of symmetry actually. Therefore, the molecule exhibit the infrared spectra. So these are IR active vibrations, right? See, homonuclear diatomic molecules, oxygen, hydrogen, nitrogen, and halogen. Halogen, in the case, you can take fluorine, chlorine, bromine, iodine. So, elements, they are homonuclear diatomic molecules. They are oxygen element, hydrogen element, nitrogen element, chlorine element, fluorine element, bromine, iodine elements. If they undergoes to the stretching vibration, even they undergoes to bending vibration to happen, definitely molecule has to contain uh, three atoms at least in it. So here these molecule, they undergoes to the stretching vibrations. So the stretching vibrations are symmetrical stretching vibration, asymmetrical stretching vibration. Of course, whatever the stretching vibration might be, they won't exhibit the IR spectra because both of them are same elements bonded with a single covalent, double covalent, and triple covalent bonds. In a case of hydrogen, a single covalent bond we will find. In a case of oxygen, a double covalent bond between two oxygen atoms we will find. In a case of nitrogen, there will be three covalent bonds, a triple covalent bond between the two nitrogen atoms. Of course, but the atoms are same. No more electronegativity difference we will find there. So we won't find any electronegativity difference. Once the electronegativity difference is not there between the atoms of molecule, no more dipole momentum value will be there for the molecule, so that they are IR inactive. They are IR inactive. In a case of heteronuclear diatomic molecules like hydrochloric acid, hydrobromic acid, hydrogen iodide, and these are very simple examples that we have discussing about. Generally, the big molecules nowadays, the huge number of new molecules will be preparing. New molecules have been preparing by the research scholars in the laboratory, even scientists also. Definitely, they will go for the recording of IR spectra for that molecules to identify the functional groups present in that prepared compound, final compound, and according to that, they will get the information regarding to functional groups. That is okay, but to explain the selection rules or what kind of molecules they exhibit the IR bands, just we have taken very simple examples. So heteronuclear diatomic molecules, hydrochloric acid, hydrobromic acid, hydroiodic acid, okay, even nitric acid, NO, and carbon monoxide, they are also IR active. So they will exhibit the bands. Hydrochloric acid, for suppose if you see, chlorine anyway is a more electronegative atom, its electronegativity is 3.5. Hydrogen atom's electronegativity is 2.1, less electronegative atom. So the dipole momentum will be slightly situated. Of course, the molecule contains the dipole momentum, and the electron density moves towards the nuclei of chlorine atom in the in hydrochloric acid molecule, so that the molecule undergoes to the vibration and it will exhibit the band in infrared spectroscopy. Similarly, so heteronuclear diatomic molecule, they are IR active. With this application, we can say that the vibrations are the molecules which are having dipole momentum, they exhibit the spectra in infrared spectroscopy, even though they are having the dipole momentum, but during their vibrations, there will be change in the dipole momentum of the molecule, right? These are IR active. Dipole moment is greater when an electronegativity difference is more between bonded heteronuclear diatomic molecules. Yes, for suppose if we take an example of hydrofluoric acid, the electronegativity difference will be 1.9. Electronegativity difference between hydrogen and fluorine will be 1.9. If a more electronegativity difference is there, then more dipolar the molecule will be, so that intense peaks we will identify, intense bands regarding to that molecules containing more polarity difference, they will exhibit very intense bonds in infrared spectroscopy. HF molecule, yes. HF 2.1 is electronegativity of hydrogen, 4.0 is electronegativity of fluorine, so that if you subtract the value, then we will get to 1.9. No, it is not. The electronegativity difference is not 3. It is just 1.9. Right. Let me correct this value. Chalo. Right. So more dipole momentum, then we will get more intense bonds in the IR spectroscopy. So electronegativity difference between hydrogen iodide is 0.4, because iodine electronegativity is 2.5, hydrogen atoms electronegativity is 2.1. So 2.5 minus 2.1 is equals to 0.4. So less electronegativity difference is there, so molecule contain less dipole momentum, therefore less intense bonds observed regarding to this kind of molecules in infrared spectroscopy. Right. So yeah, before going to learn about different kinds of vibrations possible in organic molecules in infrared spectroscopy, even in organic molecules also they will exhibit the same kind of vibrations. There is no difference for vibrations of organic molecules and inorganic molecules. Every molecule will undergo these possible different types of vibrations. So before going to discuss about that different types of vibrations, let us discuss what are IR active vibrations, or what is which one is IR inactive vibration regarding to carbon dioxide molecule. Let us see. So here there are four possibilities for carbon dioxide to participate in vibrations. In order for molecule to absorb infrared radiation, vibration at same frequency as in a light, but also must have change in the net dipole momentum as a result of the vibration. Yeah, that is a point I am discussing. See, whenever the molecule is undergoing to the vibration, there must be change in the dipole momentum. Of course, if the molecule undergoing to the vibration, even though there is no change in the dipole momentum of the molecule, whatever the dipole momentum is there initially, after vibration also, during the vibration also, the molecule's dipole momentum does not changes, that molecule will not participate, that molecule will not exhibit the spectra or absorption bands regarding to that vibration in infrared spectroscopy. Yes, so there must be change in the dipole momentum of the molecule. The dipole momentum is indicated with mu. Mu. So here you see the middle one, the ball which is indicated with blue color can be considered as carbon, whereas the other two balls connected with the blue ball, they can be considered as oxygens. So it would be a double bond. This is the carbon oxygen double bond and carbon oxygen double bond. So in this manner, if a molecule undergoes to a symmetric stretching, the molecule is participating in stretching frequencies, stretching vibration. So the symmetric stretching is happening. The symmetric stretching means uh, one terminus, right side oxygen atom is moving away from the central carbon atom with somewhat distance, and during its vibration, stretching vibration, even the left side oxygen atom also moving to the same distance what the right side oxygen atom did during its stretching vibration. So there won't be change in the dipole momentum of the molecule. So mu is equals to 0. The dipole momentum is equals to 0. This type of vibration. Of course, molecule is absorbing the energy, is undergoing to the vibration, but the vibration is not bringing any dipole momentum change. Therefore, mu is equals to 0. We cannot observe the absorption band regarding to this symmetrical stretching vibration of carbon dioxide. Right. So here you can see the right side atom is departing from the central carbon atom, and whereas the left side oxygen atom is moving closer to the carbon atom. So the stretching vibration is taking place one side of the molecule. Therefore you will find the change in dipole momentum. Net dipole momentum will not becomes zero. It is IR active. Even in the case of bending vibration also. Yes. See, uh, here the both oxygen atoms. It's a yeah, triatomic molecule. The middle one is carbon, terminal atoms are oxygen atoms. So they are undergoing to asymmetric bending vibration. During this bending vibration, uh, uh, middle carbon atom is coming up, middle carbon atom is coming up to the plane, whereas the bonded oxygen atoms, they are going down to the plane. It causes a change in net dipole momentum of the molecule, so that it is also IR active. Here also one more vibration, bending vibration is performing by the molecule, where the dipole momentum is greater than zero. This band is also IR active. So this is about the selection rules of IR spectroscopy. Yes. So today, in today's class, we have discussed about the molecular vibrations, where we have discussed about unharmonic motion of a covalent bond in molecules. So at what time, at what situation that unharmonic oscillatory motion motion adapted by the molecule, and what are fundamental bonds and what are overtone bonds also we have discussed. What bands are allowed, that after we have discussed about center of symmetry of the molecule, that after we went for the discussion regarding to dipole momentum. After that, the selection rules we have learned, selection according to the selection rules of infrared spectroscopy. uh, the vibrations which causes the change in dipole momentum, they only exhibits the absorption bands in infrared spectroscopy of organic molecules or even another molecules also. There must be change in dipole momentum. Yeah, these are the information we have learned in today's class. Tomorrow, let us discuss about different types of vibrations. What are that, and what kind of changes we will find in a molecule during that vibrations. We'll discuss in tomorrow's class. Thank you very much.